Siegfried Foessel from Fraunhofer IIS. What does IIS stand for?
Institute for Integrated Circuits.
There you go. Tell us more.
Yeah, thank you very much, Chris. So I'm heading the department Moving Picture Technology, and 5 years ago we decided to establish a new group called Computational Imaging, mainly targeting light field technologies, because we think that this is one of the next future trends. So I will go through the slides very quickly. Probably I cannot so speak so fast like John, but nevertheless, I think I even start maybe more with principles. So let's first question what kind of data representation is necessary for light field, and what are the principles behind light field. So first of all, if we have a scene and we have to capture an image, so we have a light ray in space, and in one specific point in space we can see that there are light rays coming from different directions, and this defines this light field in X, Y, Z, and direction theta and phi. And a pinhole camera, for example, is an ideal camera for capturing a light field on one point. But it's clear that we cannot have billions of pinhole cameras. This would be not very efficient. But if we could capture all of this light field, means all of the light rays, then it would be possible to reconstruct any image we can capture in a space. So with a larger hole, we collect, of course, more of the light rays. And this is how today's cameras are working. So today, however, we also add a lens, so to refocus some of the light rays. And you can say a standard camera today is more or less something like a localized light field cameras. That means on a specific position in space, you capture some of the light rays and to make an image of the light field at this point. And it's dependent, of course, today on the iris, the aperture, means how many light rays you capture, on the focal length, so from which direction you capture the light rays, and on the exposure time. And it's rebundled on the focal point. So in principle, there are different ways to get let's say, denser capturing of light field. So to separate the direction, like John already explained. So one is a microlens array with only one sensor. This is so-called insect eye cameras, or the main lens with multiple sensors and microlens arrays, or camera arrays in fixed arrangements, or let's say last step would be freely positioned cameras in a high density, and to reconstruct all of the light field. In any way, you have to make a compromise between the captured space of the light field, the density of the sampling, and the necessary computation, it's clear. So there are different advantages and disadvantages for all of these aspects. If you have a dense sampling with microlens arrays, of course, this allows you, I would call it a easy data processing, even if the data amount is really huge. But you can even calculate images without depth maps calculation by combining different images from different shots. And it avoids clearly artifacts as no light rays are missing. With the sparse sampling, means mainly camera arrays, of course, this allows you to capture a larger space. So your dimensions of the, let's say, light field captured space is larger, and it enables more flexibility for visual effects, mainly for viewpoint calculations. So why do we want to do this? Of course, we have today this typical 2D planar images, so we can watch this on standard displays. But at the end, of course, we want to have something more like a 3D positioning. We want to look behind objects. This can be done either with autostereoscopic displays, or with light field displays, or with VR glasses. So at the end, of course, we want not to look only for VR glasses looking 360 degrees around. We only also want to have 6 dimensions of freedom, means moving the head to the left and to the right, and having a real impression of being in the real world. So what does this mean now? Of course, we have the need typically to have more special effects in moving picture technology. We want to have a best description of reality by the natural content. But the natural content today does not provide this editing flexibility. We have not this 3 dimensions today. But we want to get this. One of the solutions we also consider is to have camera arrays. So you can look at this like you capture a world which is 3 dimension, and you look through a window by this camera array, and you capture this light field, let's say, spanned by the window, and you can then have a good impression what you can get. So what can you do with this? John mentioned this already, so I will go through this very fast. Of course, you can reposition the camera in X, Y, Z direction. You can have some special effects, and you can also make different depths of fields. You can make relightings, and we experimented with some of these visual effects. We started with stop motion production with 16 cameras. So here is a first step. So we had 16 of these different stop motion movies, and then we recombined this and also added virtual refocusing and also virtual movement. So the camera movement here and the refocusing is completely done by computational processing. So what is also possible, of course, you have then this objects with X, Y, Z positions, and you can also then integrate this into computer-generated let's say dimensions, and you can add, for example, virtual lights in 3 dimensions into this, and you can also work on, so you can use it for relighting of natural content. So how is this workflow going on? In our case, of course, we capture the images with camera arrays. We make some processing like calibration, rectification. We calculate, this is necessary at least for the sparse camera array, we calculate depth maps or disparity maps first, which correlates to depth maps. And after this, we can also create point clouds and render this back to the images, either to a 2D planar image or to a 3D image. So we experimented with different camera architectures. We had on one hand side our portable camera array for the sparse capturing. On the other hand, we also had a camera robot system, so where we have only one camera, so that it can be used only for static scenes, but it can have a capturing of 4 meter by half a meter with 1 millimeter distance, so that you can really capture a dense light field. You can calculate what this means. So typically, if you capture this with a distance of 1 millimeter and 4 by 0.5 meters, so you end up with 50 terabyte per image. But nevertheless, this is not the end goal, of course. For us, it's more important to have a ground truth data set to see how dense the light field should be. And afterwards, we want to evaluate what is the best solution for the camera array, how dense should the camera array be for which dimensions. So we had also made different other processing steps. One here is with a master camera and a camera array, so to get the depth information and apply this to the master camera image data. So we shot this with, together with a media university in Stuttgart and made a test movie out of this. But you see there are different advantages and disadvantages. On one hand side, we have really with this sparse camera array sampling only a few images, and you have to create very exact depth maps. On the other hand side, if you have this dense sampling, you get a really high quality directly from the camera capturing process, but you have, of course, this huge amount of data which you have to process. So we have heterogeneous architecture, different image sizes, different bit depths and color spaces, so we are working on this more and more. So here is one of the examples how we work in the rectification. Of course, we have to correct all of the image data so that they are on one line or one column. To calculate the disparity maps means we have to make the calibration of the camera to calculate the intrinsic and extrinsic parameters and to get good images out of this. But this is not an easy task, I have to say. So, of course, we also have to add metadata to this because we have to know, at least it helps if you know which positions the camera have, how many cameras you have, what are the distance, what are the time codes, what is the focal length, the pixel size, and so on. And it helps then to interpolate or to calculate a dense light field from a sparse light field. That means we use this depth information then to interpolate in between the different views and calculate this dense light field out of it. In our case, we use this to make then a depth image-based rendering. So the depth image-based rendering by itself is not very difficult. So it can be done in real time, but what is very difficult is to get really exact depth maps. Yeah, what else have to say? Okay, we work in the moment with different camera setups. So we capture with 10 by or up to 16-bit. We work in the rectification and following steps with 16-bit or floating point. We have resolutions for the camera arrays from 2K to 4K. Here a calculation for a small camera setup with 6 cameras for 100 frames. This is a 5K material. So you can see even for this 100 frames we capture 45 and only 6 cameras. We have 45 gigabyte. And if we go through the processing steps, it increases, of course. At the end, the final image is then only a typical 3.5 megabyte image, but you see this quite huge difference between the captured data and the final output data. However, you can, of course, render as much as you want from different viewpoints and different focal points. So in our case, we use this depth-based approach because this leads to significant data reduction. So the interpolated views are done by computation. So, and this reduces the data. Here you see an example which was captured from the robot system. I think it works quite well. And what is important with this, let's say, raw camera images and this depth maps, you can do this real-time processing on VR glasses. We have done this in our lab already, so that you can really capture these different views. Of course, this quality is not the best here in the moment, but I think it's important that you can have now also this 6-dimensional freedom VR, so looking around a scene or objects and not only, let's say, looking 360 degrees. So in our demo system, of course, we used a graphics card, we used typical standard off-the-shelf systems. What is important, however, I think what helps is at the end, at least for the depth maps calculation, it would be good to have really high processing power, because in our case, to calculate the depth maps for one frame needs, let's say, 1 to 5 minutes, and so it's better to transfer the data first into the cloud and to process this to get faster results. We have created a test movie with the University of Stuttgart, it's called Coming Home. It's also available on Vimeo and on our website. I think what's important here is to say we have different modalities for the data representation. We have the light field data, more or less the planar image captured from sensors. Then, in our case, we go to depth maps or depth representations. We can also transfer this to point clouds, and at the end, we can render it back to planar images. So, and as you can see in this example, of course, based on this, let's say, transformation steps, you can separate then the data points based on different parameters like the sea distance, or you can remove data elements based on other selections. So in this case, we also added additional lights to this and had a good also reflectance on the objects. So what is important is that we are merging more and more computer-generated images with real live images. So the conclusion is quite easy. So we have new visual effects possible. We have this different architectures. We have different options how we calculate this different data. We can use this disparity data or depth maps. We can use point clouds. I think what is important is how we can transfer at one point one representation model to the other representation model. We also developed for this test movie, similar like Lightro, a plugin suite for Nuke, and we have a lot of beta customers who are testing it in the moment. In our case, however, it's a little bit more difficult because we are not offering the camera system by our own. So that means it's necessary to set up a camera system, and as you see, I think the minimum is at least 9 or 16 cameras, and this is not easy if you use this with 4K cameras. Okay, that's for it. Thank you very much.
Believe it or not a laser question. You obviously have the ability to do scene relighting. Is that only an additive process? In other words, you can only lighten areas of the film, or can you delight a scene such that you could shoot it in bright light and then create a dark scene?
You can use both. However, it's limited, of course, on your dynamic range of your capturing system. If you, let's say, do not have the dynamic range in the dark areas, you cannot get it to really good quality in the highlights. But in principle, you can use this. What is a little bit more difficult, and this is what we are investigating, to define the BRDF function, means the reflectance function of the objects. You have maybe seen in this calculation we have used a standard BRDF function, so it looks a little bit artificial. So, but it can be improved, so that's only a question of the computation.
Thank you.
Now, let's say you've got 6 cameras, how do you store that data? Do you store it as raw files for each camera, as ProRes files, or some combination?
Yeah, in the moment we store it as raw data files. So some of the captured data were captured with GoPro cameras, so even in H.264 captured. However, what we have seen is to get really good resolution is that you need, let's say, an uncompressed data stream at the beginning, so that you have the full pixel alignment.
Okay. Now, have you thought about ways to reduce that data load? I mean, there's a lot of redundancy there, obviously.
That's true, yeah. Not yet, but this is for sure something what we have to investigate in the standardization committee. So I think that what JPEG and MPEG are working on then later.
Okay. Yeah.
This is a query, not a challenge. Why Nuke? Why not Premiere, Avid, Final Cut? One of them, they're popular boxes.
Yeah,
Why'd you do Nuke first?
that's quite an easy question. So we started with Avid at the beginning. However, especially for this, let's say, spatial representations, we need a toolset which has already something like point clouds or 3D representations in it. And it allows us already to use some of the existing functions which are not available in Adobe or Avid.
Thanks.